I wanted to introduce our first speaker of the day. It's Dr. Glen MacDonald. He's Distinguished Professor and Endowed Chair of Geography at UCLA. He's Director of the White Mountains Research Center and former Director of UCLA's Institute of the Environment and Sustainability. Glen is a climate scientist, is author of over 160 scientific and popular press pieces, and an award-winning book on biogeography. Glen is a distinguished member of the National Academy of Sciences, a fellow of the American Geophysical Union, and a fellow of the American Association for the Advancement of Sciences. Most importantly, he's a resident of the great city of Thousand Oaks. He's here this morning to share some of his important research on climate change and the environment, particularly as it impacts droughts and fires in our region. It's a great pleasure for me to introduce Glen. Thank you.
I'm going to try to give a bit of an overview of where we are in terms of climate change and how it relates to the drought that we experienced and also some of the fire activity we've seen as a broad stroke picture. And this is going to be science, just the science here. But let me just start with the megadroughts, megafires that we've been experiencing, sort of where we are and where we might be heading. And this is a wide geographical perspective and also a deep time perspective on this. I'm going to base this on a lot of sort of work I've published scientifically, but also popular press pieces that I've written, opinion pieces and things like that, magazine articles, and articles which have appeared in the popular press about the work that we're doing and some of the research we've done. So you can, if you Google some of this stuff, you'll be able to follow it up, either scientific literature or in popular press pieces. I want to just do a little recap of where we were in 2016, the drought that we all experienced. It was international in terms of its coverage. And these are little maps from the U.S. Drought Monitor. Areas which are red and brown are extreme to severe drought. And then any areas that are the yellow and the buff color are also areas in drought. And this goes from 2012 to April of 2016, more or less the end of our water year. And I want you to notice that each one of those years, California is pretty much 100% in drought. And if we look particularly at the southern portion of the state, we are in exceptional drought. And notice how it sort of intensifies up to 2015, and even in 2016, very, very severe drought in the southern part of the state. So that's looking at this then at a wider view. I also want you to notice how that drought was not confined just to the state borders of California, but spilled over in the adjacent Southwest and the Colorado River Basin there. Now, this was not our first rodeo in terms of droughts. The state has experienced these throughout the historical period and indeed in the prehistoric period, as we'll see. And we have an amazing water infrastructure. It would make the ancient Romans envious in terms of our reservoirs, our canals, our aqueducts, and the way we conduct water. And yet, as you may know, when we get into the beginning of 2016, beginning of that water year, our reservoir systems in this state, our internal water, was very sorely tried. Extremely, extremely hard pressed. We had reservoirs which were somewhere down about 19% of the capacity they should have been at that time. It was that way from Northern California to Southern California. So despite the massive storage that we had, our surface reservoirs were depleted. They were in a very, very dangerous state. And there's a picture of one there. That's San Luis Reservoir, where water transferred out of the Bay Delta is then stored and then comes south to us. And you can see it almost looks like a desert with just a little pond at the bottom. Now, as all the part of our water portfolio, which is very, very important in the state, is groundwater. And we could see then that groundwater resources were also severely strained by that drought. This is a map of well failures in the San Joaquin Valley. We had something like 1,700 cumulative well failures by the time we started moving into 2016. There were over 1,500 programs where there was bottled water being distributed because of a failure of well water. We did not experience that here, but there were communities in the Central Valley, particularly poorer communities, small communities, which simply had a complete failure of their wells, and they had to depend on imported water for drinking. There were many, many households that were affected by this. Now, up until recently, we did not have a statewide monitoring program to look at how bad our groundwater situation was. In other words, how fast were we pumping this water out of the ground relative to how quickly it will be replenished? That's called water mining. So how do we monitor that if we did not have then an organized system of monitoring all the wells in the state? Well, interestingly enough, you can get an idea about this from space, and you can use what's the Grace satellite constellation. It's 2 satellites have very, very precise laser instrumentation that can tell exactly how far apart these 2 satellites are. If there's a portion of the Earth's surface which has higher gravitational pull, for instance, an area where you have a lot of groundwater, a large aquifer with water, the lead satellite will move a little bit faster as it enters that gravity field. The distance increases. Then once you get over an area which has less gravity, they come together again. And you can actually map then surface and groundwater intensity from space. The resolution is coarse, about a 250 by 250 kilometer square or pixel. But these are the Grace images from 2011, 12, and 13. The red are areas where Grace is detecting a depletion of groundwater principally year by year by year. And take a look at how that bullseye centers on the state. It's just amazing. Based on these estimates then, they estimated that about 11 trillion gallons of water, that's about 300 million acre feet, was needed to address this deficit. Now, if we take a look at the whole state, we only get about 200 million acre feet of precipitation in a year anyway, and of that we might only capture at best 75 million acre feet of unimpeded runoff. We do not capture that today. So this would be years and years and years to replenish the groundwater deficit that we've suffered in the state over the course of the drought. So that simply hasn't ended. The other important part of our water portfolio of Southern California is the Colorado River Basin and, of course, Northern California. But Northern California is challenged by this drought. What about the Colorado River Basin? Over 50% of the applied water in Southern California comes from the Colorado. Most of that going to agriculture, Imperial Valley, Coachella Valley, the Palos Verdes Agricultural District. That grows the food that we eat. 2/3 of the winter vegetables for most of North America comes from that water. So very, very important. We are allocated then 4.5 million acre feet of that water. The total allocation from the Colorado River is 16.5 million acre feet. That was allocated, and as you can see, 1 million acre feet up to Wyoming, 2.85 to Arizona, only 0.3 million acre feet to Nevada, for southern Nevada. We get over 4 million acre feet. Why is this? The water was allocated based on measurements of flow from about 1905 to 1922. In 1922, we were the most populous state in the Colorado River Basin, and we had the largest agricultural productivity. It seemed sensible then to give California the largest share of the water. It had the highest demand. No one envisioned that southern Nevada would have a fake Eiffel Tower and the fountains of Bellagio. Las Vegas wasn't even a dream in someone's eye. So they didn't really realize how much water southern Nevada might end up requiring or wanting at that time. So we got the lion's share of the water, and every year 16.5 million acre feet is allocated. Now, so that's our safety net, right? However, that allocation of water, that occurred during this period, 1905 to about 1920. This was a period of unusually high and stable flow on the Colorado River. So they said, okay, average flow about 17 million acre feet here, a few little droughts, but not much. If we allocate 16.5, that's sustainable. that's pretty reasonable. But look what happens as you get more and more records of the flow on that river. There are much, much deeper droughts, and that base flow is very, very high. Look what else happened, of course. We have the amazing growth of the urban centers in Los Angeles, Phoenix, Las Vegas. Demand is going up, and we look at then, now that we have over 100 years of flow, what the average flow of that river is? It's only around 15 million acre feet. So we're allocating 16.5 million acre feet of a river that has an average annual flow of 15 million acre feet, maybe slightly less. So is this a great lifeline for us? Let's look what happened during the drought. The whole Colorado River Basin is suffering from drought. We now know it's very, very sensitive to high temperatures. This is the level of Lake Mead. That's the canary in the coal mine. That's how the Bureau of Reclamation manages the reservoir systems on the Colorado. How much water they can keep in Mead, that tells them about the health of the Colorado River system. This is when Mead was filled, Hoover Dam was completed. These are variations that occurred. Here's the beginning of the 21st century. Despite the best management, and the Bureau of Reclamation engineers are excellent water managers, despite the best management, you can see that there's a long-term secular trend of that river flow dropping down. When we came into then 2015, 2016, it was at 1,075.55 feet above sea level. That was the elevation at the top of the water there. If the Bureau of Rec estimates that the following year that water will drop and be held below 1,075 feet, that triggers a level 1 water scarcity or water shortage declaration. If that is triggered, the water allocations must be cut by 4.4% to the lower basin states. Arizona would lose 11% of its water. This is the water, folks, that supplies Maricopa County, Phoenix, and Tucson, the most populous areas of Arizona. Nevada would take a 4.4% cut. This is the water that supplies Las Vegas and southern Nevada. Mexico, a 3.3% cut. This is the water that grows crops in Mexicali, the Tijuana Valley region. So these would be huge cuts in a time when we're already in drought. California, no cut. Why would that be? Because the state has the senior water rights. Would California actually allow that to happen? It's doubtful that the current government would not want to contribute so that the pain was not so severe for the other jurisdictions. But legally, it's not necessarily the case that they would have to. That's how close we were. Now, it did not happen, but we are very close. Right now, in a sense, we're really, really playing with potentially very, very difficult situation for water resources. So we can't count on the Colorado either. So why is this drought so severe? This isn't the first one we've experienced. Clearly, we know that, over the entire historical period, there have been important deep droughts. If we take a look at California precipitation, and I'm looking at kind of our major portion of the water year, November to March precipitation. This is 1900. This record starts just before the beginning of the 20th century, and this is playing it out until we get up to 2017. And what I want you to notice is, here's the drought we're talking about. Absolutely, there are a number of years of below average precipitation. This is average precipitation. But that does not strike you as being particularly deep, right? I mean, it doesn't jump off the map at you. Our winter precipitation is in drought, but it doesn't immediately sort of hit you in the face and say, oh, okay, this was really a record breaker. Because in terms of precipitation, there might be ways you parse it. If we look at precipitation from December 17th to February 18th, this was record breaking. That might be true. But if we take a broader look at the water year, no. It was a deep drought, but it was not a record breaker. Also, I want you to notice, there's no significant trend. There's no downward trend in precipitation over the state over this time period. So what explains then the ferociousness of this drought? Well, maybe we could take a look at temperatures. Remember, the higher the temperatures, the higher evaporation rate. Evaporation rate is a nonlinear, it's an exponential relationship between temperature and evaporation rate. So as temperature goes up, evaporation rate goes up like that. The higher the temperatures, the more quickly the water evaporates, the higher the transpiration rate from leaves, the greater the water demand. The faster water is lost from reservoirs, from river systems, the Colorado being really sensitive to this in particular. Take a look at the trend in temperatures. Incredible trend in temperatures. Take a look at the drought period that we're talking about. We have a number of years within that which are record breakers, off the chart in terms of California temperatures. And it's part of a long-term trend that we can trace back to the beginning of the 20th century, which has really been exacerbated in recent years, coincidental with the drought. Now, we can put then the evaporative and transpiration demands, the soil water loss, with the precipitation, and we could look at this drought that way, using something called Palmer Drought Severity Index. This is the Palmer Drought Severity Index, which includes terms for evaporation as well as the amount of precipitation which flows into the system. And what you can see here, when we look at the recent drought, you can then see that it's a record breaker. You really can't understand this drought without understanding the temperature part, that this is a super hot drought, and this is what really has helped exacerbate it. It was a precipitation drought, but really it has been exacerbated then by these very, very high temperatures. Now, it's not just water resources that we're seeing really interesting trends and things happening. We're also seeing this occurring with fires. And there's many other things, but I'm going to focus on wildfires now. We just came out of the Thomas wildfire. We were breathing the soot from that. If you could go up to near Sunset Hills, you could see the flames surrounding Ojai on the ridgeline, okay? We experienced that. My daughter lived in Santa Barbara. Her company she worked at was closed. She was wearing a bandana around her face. We experienced that fire. We know what we're talking about. Now, that fire wasn't just big in terms of our county. That was actually the largest fire recorded in California history, where we have good numbers for the extent of the fire. We have over 280,000 acres burned. That's 440 square miles. Just think about that. There's Fillmore, there's Montecito. That's the range of that fire. It's just incredible. Amazing what happened in the Ojai Valley there, though, huh? I mean, just amazing what happened there. But just get a scope of the size of that thing. It's just incredible. Now, here's the thing, folks. That's not a 21st century one-off, okay? The 5 largest fires, which we have good data for in recorded history, have occurred in the 21st century and have indeed occurred in recent years. The Thomas Fire, that's a December number, it grew from there. The Cedar Fire, the Rush Fire, the Rim Fire, and the Zaca Fire. All of these things topping 200,000 acres. Those are the largest fires we have recorded, and they're all happening in the 21st century. They're all happening recently. Now, could this just be kind of random, a roll of the dice for California, you know? Well, if we take a look, if we scope back and we look at the entire West then, and we look at acres burned in the West, this is 1970, this is data up to about 2014. You can see that there's been a long-term secular increase in the amount of area burned across the West. Not only that, if we look at fires which are 1,000 acres or larger, what we consider large fires, 1,000 acres or larger, we're getting more and more of these large wildfires. Now, in forested regions, part of this has to do with the buildup of fuel because of the suppression of small fires. That is not going to explain things like the Zaca or the Thomas Fire, which are not burning in 200- and 300-year-old pine and fir stands. They're burning in grasslands and shrublands for much of their area. So part of this is explained by a buildup of fuel load because of 20th century fire management practices, but not all of it. If we look across the West, remember I showed you that increase in temperature? What's been going on is basically our summers have been getting longer, our winters have been getting shorter, and on average we're adding about 75 fire days to the calendar, okay? Things are getting hotter faster, the soil's drying out, the vegetation is drying out faster, it's drying out more, and we're having a longer and more intense fire season, principally driven by those high temperatures, okay? And we're seeing that what we saw in California is not isolated again to California, just like the dry conditions. This is something that is being experienced throughout Western United States and indeed North America. Now, let's get to the big question. Is this a natural cycle? Is it random chance? Or is this human-induced climate change, right? Anthropogenic climate change because of increased greenhouse gases. Suddenly, we're getting political, right? I mean, but I'm a simple scientist, all right? I'm not up here giving you a political speech. And I will admit, yes, I have done events with Al Gore, right? Who is, you know, on the Democratic side, a kind of a spokesperson, an icon for climate change, and that we should do something about climate change. Any Republicans in the crowd? Okay, who's this chap here? Kevin McCarthy. He's the leader of the House Republicans. Is that not correct? I've done events with Kevin McCarthy as well, okay? I am all about science. I'm all about just the facts. I've published papers that have said, this is the imprint of climate change. Folks, I've published papers that said, you know what? This is not anthropogenic climate change. I just call it like I see it. So I'm going to tell you like I see it. This is not a political speech that I'm giving you up here. This is science, okay? Now, let's take a look at where we are with CO2. And this is Mauna Loa, Hawaii, right? It's fantastic. You could, if they get a snowstorm up there, snowboard, go down and surf outside of Hilo, right, the same day. Fantastic. You know, very, very high elevation here, site. And there's a great observatory up there. And one of the things they observe there is how much carbon dioxide is in the Earth's atmosphere. Why do they do it up there? Because it's remote from any local sources. It gives you an idea of the background amount of CO2 in the atmosphere. And this is the record we have. And I'm proud to say that the technology to measure this minute amounts of carbon dioxide in the atmosphere was developed at Scripps Institute, University of California, San Diego, by a fellow named Charles Keeling. And so, in fact, there's a person in the audience here who knew Charles Keeling. So this is California technology. But in the late 1950s, Keeling developed a way to measure CO2 in the atmosphere, and he began to measure at Mauna Loa. These measurements are now taken at remote places around the world, remote Pacific islands, all the way to islands in the Arctic or on the Antarctic continent. And here's, for instance, the array of sites where this is done in the Pacific Rim Basin. And here's what we can see. When they first started to take the measurements, the amount of CO2 in the atmosphere was a little bit over 310 parts per million by volume. I took a look today. We're at about a couple days ago, we're about 412 parts per million by volume. There has been then, since the 1950s, a long-term inexorable increase in CO2 in the atmosphere. There's no way to argue against this. This is just the way it is. There are many, many, many observations made of this, many different countries, many different locations. But is this just part of some natural long-term cycle? Is it really unusual to have CO2 up to 412 parts per million by volume? Good question. How do we study that? We don't have the Keeling bottle measurement techniques prior to the late 1950s. But we do have cores of glacial ice from places like Greenland and Antarctica. And they preserve tiny bubbles of the atmosphere. In the case of Greenland, those bubbles could be over 150,000 years old, found at the bottom of the Greenland ice cap. In the case of Antarctica, there's samples of the atmosphere which are over 650,000 years old, at the bottom of the Antarctic ice cap. So if you drill into the ice, you remove the cores, you hold it up like a kind of big victory dance, which you actually really wouldn't do that, because if you broke it, it would cost a lot of money to replace. And you can drill into these tiny little inclusions and bubbles and get the atmosphere. And what do we see? Well, we do see, this is from Antarctica, this is the Epica ice core. There are variations, natural variations in CO2. There are natural variations. But they're limited to about 280 parts per million at the maximum to 180 parts per million. So over the last 650,000 years, we have not come close to 412 parts per million by volume. And we know that this is coming from burning of fossil fuels, land clearance, and things like cement production. At the end of the century, if we are to stay on a business as usual approach, we'll be potentially up to somewhere around 950 parts per million by volume. You can see again, that's completely, we're already off the charts. That's like in a completely different record store, okay? We're just totally gone at that point in terms of how we compare to natural amounts of CO2 variation. So what about temperatures? What does this mean in terms of temperatures? If we stand back and we look at then global mean estimates of land and ocean temperatures, these are data from NASA, go back to about 1880s. This is where we are today. We've had a long-term secular trend of increasing temperature. Now, there are variations here, and some of these are caused by natural processes like volcanic activity, natural variations in the solar constant or the output from the sun. So there are variations in there. But the long-term trend, as greenhouse gases have increased, is increasing temperatures. And climate models suggest that greenhouse gases are the primary contributor to this. Look at where we are then when we get into the 21st century and the most recent drought. For what we saw in California is, again, in terms of temperature, not restricted to California. This is really following a global pattern. 2016 was the warmest year we have on records that go back anywhere between 1880 to 1850. 2014, 15, 16, and 17 were the 4 warmest. Okay, so this is not a one-off again. This is part of a long-term trend. What about our drought? Well, the fact of the matter is the low precipitation that we saw, 2012 through 2016, cannot be confidently attributed to increasing greenhouse gases. There's too much variation in precipitation. There's too many uncertainties about precipitation delivery to California to say, oh yeah, the low precipitation, that's because of greenhouse gases. You honestly can't say that. What you can say, though, is those really high evaporation rates, high transpiration rates, that is the fingerprint, the smoking gun of increasing greenhouse gases. There was a very nice analysis done by Park Williams and his colleagues, published in 2015, that said if we take the drought in California and we look at how much of that heating was contributed by increasing greenhouse gases, they concluded that somewhere between 15 to 25% of that drought could be directly attributed to increased greenhouse gases. We could have had a drought anyway. The natural precipitation variability might have given it to us. But 15 to 25% of its severity, its extra severity, was directly related to increasing greenhouse gases. So was this a greenhouse gas drought? Absolutely. In terms of temperature, it was. You cannot say that in terms of the precipitation deficit, but you can say it was a greenhouse gas drought in terms of the temperature. We should get used to it. Because if we take a look at the 21st century, this is where the path we're on right now. This is historic emissions of CO2. Okay, historic emissions of CO2, gigatons per year. These are the estimates from the Intergovernmental Panel for Climate Change. If we were to drastically stop producing CO2 now, impossible, right? If we were to have a measured retreat from high CO2 producing economy, this is this one. If we kept business as usual, this is relative carbon pathway 8.5, RCP 8.5, this is where we would get. Okay, this is where we would get in terms of greenhouse gases. Right now, we're pretty much following that pathway. That's the pathway that we're on. It is the most severe, the worst case scenario. If we look at the temperature estimates, and this was the 2013 IPCC, this is a more recent study which was published in 2017. Based on where we're going right now with CO2, we're probably going to see global temperature increase somewhere between 2 to 4.9 degrees C, with a median estimate of about 3.2 degrees C. So right now we're on the path to the worst case scenario in terms of temperature changes, in terms of how much production of CO2 we're doing. Precipitation is really, really hard to model, and the climate models vary in terms of their estimates of precipitation, but they do converge in terms of the estimates of increasing temperature and increasing evaporation. Even given the uncertainty in precipitation estimates, if we look at the RCP 8.5 estimates for the end of the 20th century, this is for 2100, the red areas with stipples are areas we're expecting to see very significant declines in soil moisture, drought conditions, right? Dry soils. We see that over the Southwest in California, we have stipples, which means high confidence that it will dry out, and we have these deep red colors suggesting very, very severe drying. Even if precipitation stays the same in the 21st century, California is drying out, and we're drying out because the temperatures are going up. What does that mean in terms of wildfires? This is a National Academy's analysis, based on National Academy's data and analysis, looking at expected wildfires. What will happen to wildfires in this state for every 1 degree increase in global temperature, right? Then sort of downscaling it to the state and saying, okay, we increase the temperature by that much, the fire season becomes longer, the intensity of drying becomes greater, and we have more, we have drier fuel to burn. Anywhere from a 74% increase to increases that are just crazy. Over 200% here, up to 300% in parts of the state. 3 times as many wildfires in part of the state for every degree that goes up. Folks, you'll clear our forests out. Our low elevation forests will simply be cleared out if we were actually to see those kind of increases in our wildfire rates. So everything we've seen over the most recent drought, the fires, the temperatures, the very, very dry conditions exacerbated by high evaporation, they're a preview of the 21st century. This is kind of, let's not think about it as a drought. Let's think about it as the new normal. Now, could it really be that the climate is going to lock in dry conditions like that for decade after decade? Could the climate really do that? I mean, could the 21st century, early 22nd century really just be locked in to dry conditions like we experienced during the depths of the most recent drought? Well, there is a natural experiment to look at that. During the medieval period, about 1,000 to 1,200 years ago, the sun was more active and there weren't many volcanoes erupting. That meant there wasn't much sulfur dioxide in the atmosphere. Sunlight penetrates more easily, and you basically heat up the planet. So less volcanic activity gives us a warmer planet. Greater solar output gives us more energy. When the two things come together, you get a warm period, and that's called, this is temperature, that's 0 years AD, this is 1000 AD, this is 2000. You have what's called the medieval warm period or the medieval climate anomaly. Natural, caused by volcanic activity, lack thereof, and an intense solar activity. What happened then during this period to California and the West? Did we go into prolonged dry conditions? This is a natural experiment to tell us what might happen. We don't have gauges on the Colorado River 1,000 years ago. We don't have meteorological stations across the state in the West 1,000 years ago. But we do have geological and biological proxies for past climate. It could be tree rings from trees which are sensitive to drought. It could be the sediments in lakes which are sensitive to dry conditions and drying out. It could be cores from the ocean. We have a whole array of different ways to reconstruct the past climate and drought going back 1,000 to 2,000 years or even longer across California and the West. And what do these things show us? they show us that, for instance, in the 12th century, between 1130 to 1180 AD, this is a period of 50 solid years, decade after decade. This is a map of drought in the 12th century. For 50 years, you essentially had drought conditions dominating the western United States. This is a map of the 21st century drawing. And you can see very, very similar. You get more precipitation here in the Great Lakes in New England because precipitation has to go somewhere. The planetary wave misses us, it dumps it here. It did exactly the same thing in the 12th century. From studies like this, we know that if you warm things up, you can indeed lock California and the West into droughts which can go on for decades, potentially even for centuries, based on some earlier really dry parts. And they cause decreases in the Colorado River flow and the Saskatchewan River flow all the way up into Canada, and significant drying out of the West in California. This has happened in the past. It's happened under natural causes in the past. We are now pushing it that way because of increasing greenhouse gases. We can also study how those episodes affect fire. And again, this is the 12th century, this is the medieval period. This is looking at the amount of charcoal that comes into small lakes. And you can see during the 12th century, that really dry period, from Idaho to Wyoming to California, you have much more intense and frequent wildfires, just like we're getting today. This is fire scars from Sequoia National Park right here in the Southern California and the Sierra Nevada mountains. A period of intense fire activity. And this is Palmer Drought Severity Index from the West during that same period. Should be no surprise then, we're getting more fires, more intense fire, larger fires. This is what's happened in the past when we've warmed things up, and it's what's happening today. So, where are we at now? We're getting close to 10. I'm just about on time, actually. But we all had a big exhale, a sigh of relief at the end of last winter, right? We said, yeah, the drought is broken, we're good, we're going to back off on our water use restrictions, et cetera, et cetera. We'll patch up the Oroville Dam, and everything's going to be great. Folks, this is where we are right now. This is April 17th, 2018. That red, it's creeping right into us. Take a look, right there, okay? Because of the high temperatures, and we did not get very much precipitation this past winter. Northern California did better. We did not do so well. We're moving right back into the drought. That might have just been a hiccup. Should we exhale? Should we back off on our water conservation measures? We better not. We better not, because certainly for this year, we're moving right back into it. Now, we might have water conservation. We may increase our reservoirs. We may have better percolation for groundwater. We may make deals for desal and pay pretty high energy costs for that unless we can use renewables. We can supply the cities of this state, and we can supply a large part, maybe not all of the agriculture or the current crops we have. We can do that, okay? I think we can engineer some solutions. But we talked, and Mayor Claudia de la Pena talked about all of the oak trees that make Thousand Oaks so special. I want to show you something. This is satellite measurements of what's been happening to the vegetation of the state. The vegetation out here in the Santa Monica Mountains, out in the southern Sierras, the Tehachapis, out in the Mojave Desert, okay, up through the Central Coast, all the way up to the Redwoods. This is what this drought has been doing to our vegetation. I want you to notice something. These yellow and brown colors here, this is where the vegetation has been browning in our state. We've been losing plants, they've been dying, they're becoming less vigorous, they're losing leaves, etc. Up in the north, the drought has not hit so hard. The vegetation has remained healthy. But this is what's going on in the south. This is how sensitive the vegetation of the state is, south relative to north. Take a look at where we are. These white spots, these are areas where since the beginning of the 21st century, we've lost vegetation cover because of fires. Take a look how many there are in Southern California. You're not going to engineer the solution to this. You're not going to go out and irrigate and put sprinklers up in the forests, in the chaparral and coastal sage of the Santa Monica Mountains. We can keep our cities going. We can keep a certain amount of our agriculture going. We can engineer that, but we're not going to be able to irrigate our natural systems, and that's where we have to start thinking about long-term mitigation, unless we want to see this all deepen. But that's the sort of topic that the senator will be able to talk to us about. Thank you all very much for your attention.